Hello, my dear students. I welcome you once again to this current lecture. In our last lecture, we studied the two important points from the chapter, that is, the calculation of this equivalent conductance at infinite dilution for the weak electrolytes. So, for this, we studied the two different methods. The method number first is based upon the Cauchy's law, and the second method is called as the arithmetic method. After that, the second point we completed, that is called as the degree of dissociation of the weak electrolyte. Now, in the current lecture, we are going to study the next point from the chapter, that is applications of conductance measurements. How this conductance measurements is useful for the different type of the calculation of that particular solution. So that we have to study how this conductance measurements is useful for the different type of the electrolytic solution. So that applications we have to study. So the first important applications for this conductance measurements is regarding the water. So it is called as the ionic product of water. How this conductance measurements is useful, so that we have to study in this first application regarding this water. So it is called as the ionic product of the water. We know very well that the water is a universal solvent. It is present in the form of ions as H plus and OH minus ion. So depending upon the conductance measurements, it is clear that the any pure water, or if we take the purest water, even though it has the some type of the conductance, even though we take a pure water, it show the somewhat conductance at a different temperature. And why this is so? Because we know that this water is considered at that time as a weak electrolyte, and if it is considered to be as a weak electrolyte, then what happens? We know that this water ionizes in the form of its ions, as if we consider this water, it ionizes in the form of its ions, as it get ionizes as H plus ion, and second is called as your OH minus ions. So this is the ionization of this water. Now what happens? This is now equilibrium between this undissociated water to that of the dissociated ions of this water. So for this equilibrium, the equilibrium constant K can be calculated as K is equal to concentration of these ions, that is concentration of H plus ions into concentration of OH minus ions, divided by the concentration of water. So by using this simple relation, we may calculate here equilibrium constant. K stands for equilibrium constant. Now the ionization for this water in aqueous solution, this ionization for this water, we can say that this ionization in terms of this concentration in aqueous solution of this water, we can say that this concentration of this water in aqueous solution remains constant, and that's why we may write the next relationship between Kw is equal to equilibrium constant into concentration of water. Why this is so? This is because in the concentration of this water in a aqueous solution will be constant. And why this is so? Because this ionization is a partial, it is a slight ionization of water can be takes place. So we can say that the concentration of water in aqueous solution will be constant, and that's why this Kw is equal to equilibrium constant multiplied by the concentration of water, that is again equal to concentration of H plus into concentration of this particular OH minus. So this is a second type of the relation between this equilibrium constant towards the concentration of particular water. Now this Kw, what is the meaning of this Kw then? This Kw is called as ionic product of water. This Kw is called as ionic product of water. This ionic product of water is there because we take into consideration the concentration of the respective ions from this particular water. Now, the aqueous solution, from the aqueous solution of this water, the concentration of this hydrogen and hydroxyl ions we take into consideration. So, the value of this Kw, if you want to calculate or if you want to determine the value for this Kw, so this value of this Kw, that is a ionic product of water, can be determined from the Colash law. It may be determined from the Colash law, and the second is important law is there. Sorry, second important data is there, that is a Head-Wheeler data is there. So from these two different aspects, we have to determine it from Colash law as well as the Head-Wheeler data. So from these two different concepts, that is one is the Colash law and second is Head-Wheeler data, we may calculate the Kw, that is the ionic product of water, and this ionic product of water from these two different aspects is obtained as Kw is equal to 1.10 into 10 raised to minus 14. So this is a magnitude of this ionic product of water for the pure water is obtained to be 1.10 into 10 to the power minus 14, and this is called as the ionic product of water. So this ionic product of water, this ionic product principle is valid in solution in which water is present. So we have to apply this ionic product of water for the solution in which this water is present, and so we can say that from this ionic product of water we may calculate the concentration of H plus. We may calculate concentration of H plus or concentration of OH minus from the solutions. So this ionic product of water value is very important as far as the determination of concentration of this H plus and OH minus ions from a solution is concerned. So this is the first important application of this conductance measurements called as the ionic product of water. So in this ionic product of water, we consider here the any purest form of the water can show somewhat conductance, and this conductance is due to the partial dissociation of this particular water molecule into its ions, that is H plus ion and OH minus ions. From this we may write here equilibrium constant, that is K is equal to concentration of H plus into OH minus divided by concentration of H2O. Now in the aqueous solution, it is to be considered that the concentration of this water in solution remains constant, and that's why we may write here Kw is equal to equilibrium constant into concentration of water is equal to concentration of H plus into concentration of OH minus, with this Kw stands for ionic product of water. So this is the ionic product of water. Now in order to determine the ionic product of water for the purest form of water is determined on the basis of the Colash law and Head-Wheeler data for the pure water. So from these two different methods, the value for this Kw is obtained, that is equal to 1.10 into 10 raised to minus 14. So this is called as the ionic product of water for this pure water, and from this, if our aqueous solution consists of this water, then we may calculate the concentration of H plus ion and OH minus ion present in a particular solution. So this is the first important application of this particular conductance measurement. Secondly, we have to consider the second application of this particular conductance measurements, that is solubility of, the second important application is a solubility of sparingly soluble salts. Solubility of sparingly soluble salts. This is a second important application of this particular conductance measurements. Now, how this conductance measurements is useful for the determination of solubility of sparingly soluble salts, that we have to take here. Now, we know that as far as the salts are present, if that salt is a sparingly soluble salt, then we can say that these sparingly soluble salts cannot be get ionized 100%, but it has the somewhat partial ionization in the aqueous solution. Or we can say that if we take the aqueous solution for this sparingly soluble salt, it may give the somewhat partial ionization of this salt. So for this purpose, from the aqueous solution of the sparingly soluble salts, the salts, suppose if we take the salts as AgCl or copper sulfate, so we have to consider these sparingly soluble salts and we have to consider their saturated solution. We have to consider saturated solution, this saturated solution of these sparingly soluble salts. Then we have to prepare the saturated solution of the salts in water whose specific conductance is already known. Means we have to consider the such a water whose specific conductance is already known to us. Now from this we may calculate here the specific conductance of the saturated solution as specific conductance of saturated solution Ls is equal to specific conductance of the salt, specific conductance of the salt plus we have to consider here specific conductance of the water. So it is the relation by which we can calculate here the specific conductance of saturated solution. This Ls is called as the specific conductance of the saturated solution. It is to be calculated with the help of this specific conductance of the salt. The salt has some type of the specific conductance, so we have to take into consideration that specific conductance of salt as well as the specific conductance of this water. So if we add these together, it is called as the specific conductance of the overall saturated solution of the sparingly soluble salt. Now after this, from this equation we may calculate the specific conductance of this salt as, if we rearrange this equation, specific conductance of this salt is equal to the specific conductance of the solution minus the specific conductance of this water. So this type of the relation is useful for calculating the specific conductance of the salt with the help of specific conductance of saturated solution minus specific conductance of the water. Now from this equation of the specific conductance of a salt, we may calculate the equivalent conductance of this saturated solution, that is lambda is equal to, once we get the value for this specific conductance of a salt, from this we may calculate here equivalent conductance of the solution as lambda is equal to 1000 multiplied by specific conductance of this particular salt, specific conductance of this particular salt divided by its concentration, that is a C. So this type of equation is used for the determination of equivalent conductance of the solution as 1000 into Ls, that is specific conductance of salt, divided by C. Now this C is called as the concentration of salt in equivalents per liter, and hence it is called its solubility. This C stands for concentration of a salt in equivalents per liter, and so it is called as its solubility. Now we know that since this salt is a sparingly soluble in a solution, this salt is sparingly soluble in the solution. Now for this purpose we may consider here is equivalent conductance. We consider here its equivalent conductance, that's a lambda is equal to its lambda 0. What is the meaning of this? We consider this salt as a sparingly soluble salt, so we can consider here this solution is a dilute up to such a limit. For this purpose we consider here its equivalent conductance is equal to the equivalent conductance at the infinite dilution, and from this for a soluble salt we can say that its concentration, that is a C, is to be calculated as, therefore C is to be calculated as 1000 into Ls that is specific conductance of salt divided by equivalent conductance at the infinite dilution. So by using this equation, we may calculate here the concentration of a salt from the given solution. So this is the final equation for the calculation of this concentration of the sparingly soluble salt present in a solution. That is a C is equal to 1000 into specific conductance of salt divided by equivalent conductance at the infinite dilution. So this is the second important application of this particular conductance measurement, that is called as the solubility of the sparingly soluble salt. Now from this second important application, it is possible for us the two important things that we may calculate here the specific conductance of a salt with the help of specific conductance of the solution as well as the specific conductance of the particular water. Then from this we may calculate its lambda also, and finally we may calculate its the concentration of the sparingly soluble salt also. So this is the second important application of the particular conductance measurement. After that, the third important application of this conductance measurement we have to study now. This third important application is degree of dissociation. This third important application is degree of dissociation. This is the degree of dissociation of weak acid. Degree of dissociation of the weak acid. So this is a third important application of this particular conductance measurement. Now in the last lecture we studied this important concept, what is in by the degree of dissociation. So this degree of dissociation is useful for the weak electrolyte, or it may be useful for the weak acid also. So from this degree of dissociation we get the idea regarding the determination of degree of dissociation of weak acid as well as its dissociation constant. So how to calculate that? So for this purpose we have to consider the weak acid as a acetic acid. We consider here acetic acid as a weak acid. Whenever we consider this weak acid, that is acetic acid, we consider here this acetic acid. So whenever this acid is considered, we know that it get partially ionized into its constituent ions. So first ion is a acetate anion CH3CO minus plus the second anion, second ion is called as the H plus. So it get ionized into its acetate anion, and second is a proton. Now from this what we have to consider here, we have to first determine the specific conductance. We have to determine first the specific conductance. We have to determine the specific conductance at 25 degree centigrade. We have to first determine the specific conductance at 25 degree centigrade for this solution of acetic acid. For solution of acetic acid, for the solution of acetic acid in a second step. The second step, what we have to do here, we have to determine now, we have to calculate the equivalent conductance, that is lambda. Once we calculate the specific conductance in the first step, in the second step we have to calculate its equivalent conductance. So that lambda is equal to 1000 into this rho divided by the concentration C. So from this we can calculate its equivalent conductance. After the calculation of this particular equivalent conductance, in the third step we have to calculate now the third important parameter of this acetic acid, that is a lambda 0. We have to calculate its lambda 0. And what is by this lambda 0? This lambda 0 is called as the equivalent conductance at infinite dilution from Coleridge law. We have to calculate it from the Coleridge law. From this Coleridge law we may calculate here now lambda 0 for this particular acetic acid. So how to calculate that? Therefore this lambda 0 for this acetic acid is equal to, it is a summation of equivalent ionic conductance, it is a L0 of this H plus L0 of acetate anion. So the summation of this particular L0 of H plus L0 of acetate anion we have to take into consideration, and from this we can say that this type of the equivalent conductance at infinite dilution for this acetic acid can be calculated. Now at this lambda 0, we consider that the complete dissociation of this acetic acid takes place. At this lambda 0, what happens? At this lambda 0, complete dissociation of acetic acid takes place. So that's why we call it as a equivalent conductance at the infinite dilution. Now once we calculate this infinite dilution, from this we may calculate now, therefore we may calculate here alpha is equal to the ratio of lambda to that of the lambda 0. What is the meaning of this alpha? This alpha is called as the degree of dissociation. This alpha is called as the degree of dissociation. This degree of dissociation can be calculated by taking into consideration the ratio of equivalent conductance to that of the equivalent conductance at the infinite dilution. And once we calculate this alpha, from this alpha, now we may calculate here the second important parameter, that is called as the Ka, and this Ka is called as the dissociation constant of this acetic acid. So it is to be calculated by Ka is equal to alpha square C divided by 1 minus alpha, dissociation constant of this acetic acid, that is Ka, is equal to alpha square C divided by 1 minus alpha, with this Ka is called as the dissociation constant. This is called as the dissociation constant of acetic acid. So this is the final equation for the calculation of dissociation constant of this acetic acid. So this is the third important application of this conductance measurements, that is called as the degree of dissociation of the weak acid. For this purpose we take here the acetic acid as an example of this particular weak acid. So as this acid is a weak acid, we know that it is present in the form of its ions, that is a acetate anion plus protons. Now for this weak acid we have to determine some parameters. So first important parameter we have to determine, that is called as a specific conductance. So that specific conductance we have to determine at 25 degrees centigrade for the solution of acetic acid. So once we determine this specific conductance, from this specific conductance we have to calculate its equivalent conductance. After the determination of the equivalent conductance, we have to calculate its lambda 0, that is a equivalent conductance at infinite dilution for this acetic acid from the Colash law, that is equal to this lambda 0 equal to L0H plus L0 of acetate anion. We have to take into consideration their values, and after the determination of this particular lambda 0, we know that at this lambda 0 complete dissociation of acetic acid can be takes place, and from this we may calculate here the alpha, that is the ratio of equivalent conductance to that of the equivalent conductance at infinite dilution, that is called as the degree of dissociation. And once we calculate this degree of dissociation, we may calculate now Ka, that is called as the dissociation constant of the acetic acid, that is a Ka is equal to alpha square into C divided by 1 minus alpha. So this is the third number application. So in the current lecture we studied the important point from the chapter, that is called as the applications of conductance measurement for the different aspects of the particular solution. The first important application is a ionic product of water. Second is called as the solubility of sparingly soluble salts, and the third important application which we just completed is called as the degree of dissociation of weak acid. So the remaining points from this syllabus we will take in the next lecture. So with this I stop here. Thank you so much.